Another application of integration that we're going to study is something called solids with known cross-sections. This is where things start to get a little bit weird because now we're dealing with a three-dimensional figure. So let's say that we have a function, and let's call it, we'll call it f of x. And now, usually when we do these types of problems, there will be a specified region. So here we have this blue, it's not really a triangle because f of x is curved, but we have this region here in the xy plane. But now, this is the base of a solid. And so what problems usually say is that let's say that this solid has a known cross-section where cross-sections perpendicular to the x-axis are, for example, squares. And so what that means is that at this point here, if we were to cut off this point, we would get a square. Obviously there's no height here, so we can't get a square. Let's pick somewhere in the middle. So if we were to pick here, we would cut it sort of vertically like this, and the solid would be, the cross-section of the solid would be a square. So if you can kind of imagine this popping out of the page, you'd go to square shape like that. If you were to cut it here, you would get a square shape like this, and notice that the square is smaller because the initial length in the base of the region was smaller. Same thing here, we get a smaller square like that. If we go bigger, notice that the cross sections get proportionally larger, and then here we get an even larger one, and then here at the very end we would get the largest one. And so you can kind of see that this sort of like doing the cross sections of this forms a skeleton for the actual shape, and the actual shape will be some sort of like curved cornucopia of calculus solid that's completely solid and filled in like this. Okay. Now, however, the question is to find the volume of whatever this solid is. And so the way we're going to do that is by splitting up this solid into basically like a cross-section. So here's how we're going to do this. Here's our function again. So when we did integration before, we can think about having we thought about having a representative rectangle. And so the area of this rectangle was equal to the height of the rectangle, which was f of x minus 0, because we're going to the x-axis, and then times the width. And the width is simply, dy. No. The width here is dx because it's a vertical rectangle, and so the horizontal piece is the small one. However, when we make this three-dimensional, this rectangle becomes, it'll become a rectangular prism. And so you could imagine a square-shaped plate, for example. And so we have a very thin square-shaped plate that would be our representative shape for this. And now what we're going to do is we're going to find the volume of this little shape. And what we're going to do is we're going to use the volume formula, which is length times width times height. Now, the width of this is the same. It's going to be dx. The length of it is f of x. And the height, because it's a square, is also going to be f of x. And so the volume equation becomes f of x squared, because we're dealing with a square. And then because we need to add up all of these square plates between here and here, we're going to go from a to b, then we're going to integrate from a to b. So this is an example where the cross sections are squares. In general, here's the formula. So in general, the formula for the volume of a solid of a known cross section is v equals the integral from a to b of a of top function minus bottom function, we'll talk about this in a second, dx. Also, this is for a dx integration, which the way you'll know it's a dx integration is that the cross sections are perpendicular to the x-axis, and it will specify that. Now, let's talk about this a thing. The a thing basically means the area function. So your cross sections could be many different things. For example, the cross-sections could be squares, in which case A is simply the top minus bottom squared. The cross-sections could be rectangles, in which case A is going to be top minus bottom times some other thing which will be specified, because it could be the height is twice the base or 3 times the base or something like that. You could do semicircles, for example. This is not often. Rectangles or squares are the most common, but if you did a semicircle, you would do A equals, and then a semicircle, you would have to take the top minus bottom and divide it by 2 to get the radius. And so your formula would be top function minus bottom function divided by 2 squared, so it's r squared and then pi. And that would be a full circle, so to get a semicircle, you would again have to multiply this by half again. So this is a complicated formula, it doesn't show up very often. Let me put these top and bottoms in here, so minus bottom squared, bottom, okay, etc. You could do triangles is another one, so, and for a triangle you would basically do 1/2 base times height, so A equals 1/2 base and then the height, and the base would be again the top minus bottom, and then the height would have to be specified just like with the rectangle case. So if it's like 7 or something else, then that would be specified. Let's also talk really briefly about the top minus bottom piece. In the original function, or the original example that we did, we only had f of x and then the equation y equals 0 for the bottom. But in general, you could have a situation where you have a top function f of x and then a bottom function, I guess we could color code this so it's better. The top function was red, and we'll call this f of x, and then the bottom function was blue, call it g of x, and then you could have, for example, let's do semicircles for this one. They would look like this, sort of popping out of the page. You get bigger and then smaller as you got closer and closer to the ends. Same thing over here, smaller and smaller and smaller. So you get sort of like a crescent shape, but it's 3-dimensional. But here, to find this, your area function would be the top minus bottom, so you'd have to do f minus g. That gets you this diameter piece, but then because you need the radius, that's when you need to divide that by 2, square it, and then throw the pi in there to get your semicircle formula. So we'll look at some examples of these and do some AP practice to figure out what things come up most often. But this is the general formula that you're going to be working with for these. Hooray!